first thing that I will look at is what I've listed here as positive displacement devices. And by positive displacement, we mean that once you have a substance taken inside a device, no matter what the outlet condition, when you operate it, it will push it out. There is no way that it will just stay inside. So the way we can do it in the real world is the most classical thing that you have come across, which is the cylinder piston arrangement. For instance, if there is an inlet and outlet on this, and this is, say, handling air or, say, a liquid, then irrespective, once the fluid is inside this, the piston will compress it, and the moment the pressure inside is more than the pressure outside, across between which there is a valve, it will push it out no matter how much pressure is there. So in the worst case, if the outlet has been completely closed, the piston will still try to push it out. If that doesn't go out, the pressure will keep increasing, then something in this will break. That's the critical thing of positive displacement devices. The other ways to achieve positive displacement is through a gear pump or a gear type of a compressor, a screw device. You have two screws in mesh, one is powered, the other is idling, and as the fluid moves along the length of the screw, the volume that it occupies in which it was trapped keeps decreasing until it reaches the outlet and is sent out. That's a screw compressor or a screw pump. The third one is a scroll type of a device. Scroll is that you have two plates, just something like this, which are sitting with one another, and one of them is rotating, the other is stationary, and in the process, the fluid gets trapped, gets compressed, and pushed out. So these are devices in which there is a negative work, that means they are work consuming devices. The other big example of positive work output is the internal combustion engine, in which the same thing happens, but there is a net work output. There could be 2 strokes or 4 strokes, that doesn't matter. One of these strokes produces the power, the other 3 or other stroke does something else to keep the machine going. So the way we analyze this, and in this course we will assume that there is no fuel coming in, is that we say that first, in all of these cases, I will define my system boundary, and the system boundary in this case is our system over there. And we know that as the piston goes up and down, the shape and size of this could change, and if there is an outlet, things could even be going out, or there is an inlet, as it comes down, it could be taking material in. If these are open, this becomes an open system. Otherwise, largely we will look at closed systems. Once we define that it's a closed system, the next thing we have got to see is what's the working substance in this. And so we write down that the working system could be this gas, or it could be a wet saturated state, or it could be a liquid, and we write down the name of that. Nitrogen, oxygen, or butane, whatever it may be. So we know that in subsequent solving, when I need to get properties, which material is there for which I should get standard data. Then it tells us that once you have decided whether it's a closed system or an open system, in this case we are looking at, say, a closed system, we know what are the equations we need to use, and we write those equations. And it's important that when we write these equations, we make no assumptions at this point, but we write the full equation. In this case, of course, mass is constant, and we know that for a closed system, we have to write the equation that Q12 is equal to W12 plus E2 minus E1, which is the first law of thermodynamics. So conservation of mass, conservation of energy, we write this. We could also write the second law equation and say, what can I say about the entropy for this system? In many calculations, this may not be required, but if we say that this is an isentropic process, then we can write down that entropy change in this is 0. Otherwise, this will be an increase in entropy. So after writing the equations, the next thing we need to do is, what are the assumptions that I can reasonably make in making this analysis? It requires a little bit of a physical feel for the machine and the problem and the real world thing. That's the best way to say, well, what is a good assumption, what is not such a good assumption. When we look at this, some things we can make clearly that this volume is small enough that the center of gravity of the system does not change too much with during this process. It may be a few millimeters, few centimeters, but not like 100 meters or something like that. Then we would have to worry about potential energy changes. So we can say that delta PE is 0 and the system itself is not moving, it is stationary. So we can say that delta PE is 0. So this is something we can put here. And the moment we do that, we know that life becomes a little easier. You can write E2 minus E1 as U2 minus U1. And we've now got the equation that we need to solve. If we know what is the heat transfer, if that has been known, if we know that it's an adiabatic system, we know that Q12 is equal to 0. In that case, this is the relation that we are left with. Then we say, well, how can I calculate work for this? And say, well, there is work being done at the piston boundary when there is a force there, and this is doing the work against what the piston does. The piston could be having forces coming on the connecting rod, or also frictional forces between the piston rings and the liner. All of that will be equal to the work done by the gas on the piston, or the opposite sense, work done by the piston on the gas. That we now know can be done as integral PdV, going from whatever the initial state was to the final state. And we need to have some relation between pressure and volume to know this. The common thing we came across was that we could say that this is some sort of a polytropic process, PV to the power n is equal to constant. This could be for a gas or even a saturated substance. And then we can say, well, how do I get the properties? And this is where we get now into two lines of action. If this whole thing were only a gas, and that's something we need to say, the working substance property, say we have a gas, and can I assume this to be an ideal gas? We are not necessarily going to keep on calculating PR and TR in every case, but largely by looking at it and say if it is air being compressed or nitrogen being compressed at ambient conditions, we can write it, but we must say explicitly that under these conditions we can say that throughout the process from beginning to end, we can assume that these conditions are such that ideal gas assumption is okay. Once we do that, we have the luxury of using PV is equal to RT and going ahead with the solution. If the problem explicitly states that there is a vapor, the word vapor comes in, or the word wet comes in, then we got to be careful that we cannot make the ideal gas assumption. The moment we come across these words, we must go to property charts and tables and get data from there. So this is an important distinction one has to make. It's a decision that we have to take quickly on, because then we will know what numbers to put in the problem while solving this problem. An example of a wet system, there are some problems that we had given in the assignment, is that say we have a cylinder piston arrangement in which we have a piston sitting over there, say, and inside this there is a certain amount of liquid and certain amount of vapor over there, and we hit this against a certain pressure so that the piston rises to some other point. So we say this is state 1, this is state 2, and we want to know what happens during this process. So here we have to go for vapor properties. If the problem says that a gas is contained here, and if by intuition we know it's nitrogen or oxygen at about ambient conditions or higher temperatures, ideal gas assumption is really perfectly fine. But if the temperatures are close to the critical temperature or even lower than that, then we have to go to this route. Please keep that in mind. Okay, so that is the way we get the properties, and then we begin solving this problem and get whatever we want. Well, it always helps to show all these processes on some property diagram. For example, here I'm going to show this process on say a PV diagram. And so where is the initial state? And say if we take the example of say a steam engine. Now we do not see this, but 25 years back and the beginning of the Industrial Revolution, this was the machine that changed the world. So there the inlet state was here. This is the topmost position which the piston can take, which you know this is called the top dead center. The bottommost position it can take is the bottommost position there, which is the bottom dead center. For some time we admitted steam, then the steam valve closes. And then this follows a series of paths, series of states until the piston reaches the end, at which point the exhaust valve opens and the steam is let out, and it is now only got steam at the ambient pressure, slightly above ambient pressure. And then it comes back, and as it's coming back, it pushes that steam out. So these are the state it goes, but now it is an open system. This part was an open system because steam was coming in. This is a closed system. We can assume it to be reasonably that it is adiabatic, and this is the outlet. Once it comes to the top, again we start exposing it to the boiler, and it again generates this. So that's how the classical steam engine used to work. So this is open system. This is closed system. And unless it's explicitly stated that there is so much heat transfer taking place between the surroundings and the piston, we can assume that this type of a device will be adiabatic. Okay, so adiabatic means heat transfer is zero. So whenever we make an assumption, we should explicitly write that I am going to assume that in this problem, nothing is said. I'll assume this is adiabatic, Q12 equal to 0, and then we go ahead. Because in the absence of anything else, there is no way we can calculate Q12. So we assume it to be 0 and proceed with the analysis. So this sets up the problem. Again, if nothing is mentioned, what type of process is there, then again we have an issue. So we'll need to again say that, okay, let's assume that is isentropic, and then get PV to the power k equal to constant, and then solve the problem from there. So there are many problems that you will come across where you have a cylinder piston arrangement like this happening. It could be that the gas is expanding, or it could be that the piston is doing work, and there could be various variants on this. For example, there could be a spring-loaded thing, or the heavy piston being put, all types of things could be there. Practical applications of this is a reciprocating device, and the most common thing is a positive displacement type of a compressor. And most refrigerators or window air conditioners would have reciprocating compressors where they compress the refrigerant and put it out. So what we had shown in the earlier picture here as this, if it were a reciprocating compressor, it would be doing slightly different things. So let me just explain how these reciprocating compressors work. So what we have done is, here's a device, and it has got two valves. One, and this is connected to the inlet, this is connected to the outlet. What this valve does is that when the pressure inside is less than the pressure here, this opens and allows the gas to flow in, or the vapor. So this is what will happen at some point. And what this valve does is that when the pressure here is more than the pressure here, it pushes the gas out. So there are two valves which do this job. So there is one process which could be the intake process, where the valve is opened up, and this happens when the piston is up here and begins to move down and comes to this point. And as it is doing so, if the valve were kept closed, this pressure would be less than the inlet pressure. But since there is a valve, that valve opens entirely because of the pressure difference between the two sides, and this thing moves in, and so the working substance fills up this space. So now the piston has reached its bottommost position, it cannot go any further down, and so what happens now is that this thing begins to move up. The electric motor is driving this. The moment it starts moving up, the pressure inside here becomes more than the pressure here. So this valve will now remain shut. And we'll have to now see what the outlet valve does. So this begins to move up, and as it moves up, the pressure keeps increasing. And at some point, this pressure is equal to the pressure here, and after that, a slight movement up here, the pressure here would be more than this pressure here, in which case this valve will open and some of this vapor will be pushed out. So this, it will keep doing it until it reaches its topmost position. So from here to here, it is an open system where it pushed it out. After it reaches the top, this pressure is equal to this pressure, this valve closes, this pressure is greater than the inlet pressure, this valve closes. Now you have a closed system over here. And then what happens? The piston now begins to move back, which was what I do first here. But in moving from this position, as it comes down to say some position over there, it is a closed system in which the pressure inside is decreasing. And it will decrease up to a point when it equals this pressure. After that, when the pressure here is less than this pressure, then from there till the bottom part, this much, it will suck in the fresh refrigerant. So there is a push, this travel when it takes in air, and this part when it pushes it out. So even though the total displacement is from top to bottom is this much, the actual amount of vapor that is taken in is less than this total volume, because there was some dead volume here already which was always going to be there, and only a certain volume is what went out. This is, so if you draw it on the pressure volume diagram, here is what we get. Now you can put PV, also capital. So at the, when the piston moves from top dead center to the bottom dead center, these are the two states. Here the pressure begins to decrease. And then it reaches a point and then it goes in. So this is when it takes in fresh gas. Then from here it begins to compress. It reaches the top pressure, and then from here this is the discharge. And this is intake. So this much of the total volume that we had, which was this much, only that much volume was actually taken in. And this ratio to this ratio is an important indicator of how this thing works. And that's how much got discharged there. So that's the type of thing it happens. These two processes I have shown dotted simply because they are both. This is the expansion process. This is the compression process. So both we will assume to be isentropic in the ideal case. If it is not isentropic, then because it is a vapor, we can say that PV to the power n is equal to constant, that n could be different from K. So we have this isentropic expansion, isentropic compression, followed by constant pressure discharge and constant pressure intake. So that's actually what happens in all these reciprocating compressors. In the case of liquids, this compression is not too much. The moment it reaches here and it starts to compress, the pressure inside becomes higher. This valve will open and it will start pushing it out. So a liquid, this much will get pushed out. In a vapor, less will get pushed out. So that's the great difference between these two devices, in vapor and the gas part, the liquid part. You do not see too many liquid type of compressors with reciprocating thing, but when you want extremely high pressures, say 200 bar, 400 bar, 1000 bar, then either it is this type of a device or what is called a vane compressor. I won't go into the details of this, but you can look up on the web and see the devices. Or gear pumps, they deliver very, very high pressures. Where would we need such high pressures? In hydraulic control systems, for example. In an aeroplane where the wings and the flaps are to be adjusted, that is done by giving force to a cylinder piston arrangement with a high pressure oil in it, and that oil pressure is, flow oil pressure is regulated by electronic controller, which gets signals from its main flight computers. So that is one example of that. Another example where you have the liquid going in and out is what you may see all your bulldozers and excavators, where the bucket goes in, scoops it out. Inside that long cylindrical thing is basically a cylinder piston arrangement in which you are putting not gas, but compressed oil into it, and that does all the work for us. So these are all analysis could be done from this type of a system. Okay, so that's the first device that we have looked at, and that is your positive displacement device. A few words about the other ones. Gears is basically like two gears in mesh, and what you have done is created a space so that this is a gear, and this is in mesh with another gear, and the space around this is very tightly controlled. There is a very small clearance between them. One of this is connected to the inlet, this is connected to the discharge, and what it does is it's trapped this fluid which was trapped here. It will be carried forward and physically pushed into this thing. So that's how you can have two gears in mesh doing the job of a compressor or a job of a pump. So these are the two external gears here. One could be one external gear, the other could be internal gear. The most common example of this is a lubricating oil pump in every internal combustion engine. You won't see any diesel engine or petrol engine anywhere which doesn't have at least one of this for lubricating oil, and possibly a second one for, in the case of definitely for diesel engines, for the feeding of diesel fuel up to the engine. So a typical engine will have two gear pumps, two positive displacement devices. Screw compressors, as I mentioned, are two screws in mesh, so the flow happens normal to the plane of the paper. Very difficult for me to show it here, but we can see some pictures of screws later on and see how two screws in mesh can be made to behave like a compressor. And these days, the reason for bringing up this discussion is that if you look at large compressors for central air conditioning devices, or things where you need very high pressures and in a very compact way, one is going for screw compressors very largely, and in some cases, even your domestic refrigerators or air conditioners will have a scroll compressor. The reason for doing this is that what I mentioned just about how this device works is that out of this much displacement volume, you are only taking in this much fresh substance, compressing it and throwing it out. The volumetric efficiency of these devices is very low. They are bulky, and screw compressors, gear pumps, or scroll compressors, they do this in much more higher efficiency. So that is the reason why they are used, and they have already become much more popular than reciprocating compressors. So that's the reason for bringing it up in this discussion. That one must know that yes, you go to buy a fridge or an air conditioner, will say that we have a scroll compressor in this air conditioner, which is more efficient than a reciprocating compressor. The geometry is a bit complicated. I suggest you only way to understand the geometry is, I made this a cartoon out here, but you actually have to look at the engineering drawing of these devices to understand what are the very fine points by which these devices are made.